Okay, so with that, I'd like to go ahead and introduce our speaker. Robert Lee is a professional engineer, and he's the Director of Flexible Pavements at the Texas Department of Transportation. And today he is going to be sharing with us some of TXDOT's experience with balanced mix design. And with that, I'll go ahead and hand it over to Robert.
The conference has been unmuted.
Can everyone hear me now? Amy, am I being heard?
I believe so.
Okay, all right. Just wanted to make sure.
Go for it.
All right. I just wanted to say thank you for giving me the opportunity to talk for just a little bit about our balanced mix design approach that we're using in Texas, or trying to get to the point of using. Got a lot of pieces that have come into place and a lot of research going on to support this effort. Before I get started, I'd just like to give a shout out or some thanks to Shane Buchanan of Old Castle Materials. I've known Shane for a while, and he helped brainstorm and kind of help us kickstart our program here in Texas. We kind of had some initial thoughts of what we wanted to do, but he was really the one that kind of help jumpstart that or get us started in the right direction. I just wanted to give him a shout out and a thanks. So with that, I'm going to jump right into it. And I've given this presentation several times within the state, and some of the things that we talk about, some of our initial thoughts were pretty close to what everybody else is going through in the country, and some of these things cross a lot of boundaries. And so in Texas we have dry mixes where they're prevalent here in our state as well as across the country, I'm aware of, and we've done a lot of things in our specifications to try to address those. And so lowering in design, we've done that. We've raised lab molded densities, and we've realized that only helps so much. Continuing to increase binder replacement without addressing mix performance, we realized that really wasn't very sustainable. We went through that where we were back in a money crunch, and we were really looking at just extra money for roads and not really looking at long-term performance. Our specifications have gotten really restrictive over the years, and they're very large. They're about as large as I would like them to be. So and then once we get specifications in place, we come back and we put a bunch of general notes on those specifications to try to address loopholes or things that were not, fully giving us what we wanted or what we think we want. And so those really are not long-term solutions. We're coming to realize that. And what we really needed to do was increase our understanding of the factors that drive mix performance, so we can help us to better optimize our mixes. This is a national problem. We've seen this, and I've talked to a lot of folks around the country when we were trying to get started and trying to pick their brain and see what they were doing. There's a lot of studies out there, including NCAT track. Texas Transportation Institute has done some work. TTI at Texas A&M University has done a lot of work. There's a lot of things that NAPA are working on, and also NCHRP's got a panel now, and they're actually looking at this balanced mixed design approach or optimized mixed design. You'll hear a lot of words: balanced, optimized, engineered, but it's basically kind of the same thing. So as we get into it, I will get into the details, but you'll hear kind of different terminology, but it's basically all the same thing. So one of the things we wanted to do was kind of ask ourselves some questions when we went into this. And if you know a little bit about Texas, we're probably one of the last states that hasn't fully implemented over to Super Pave. And I knew going into Super Pave that would probably get us a little more asphalt in our mix, get us a little more durability. But is Super Pave the answer? And looking across the country and seeing that everyone, or not everyone, but a majority of people are still having some of the same issues that we're having, probably not the ultimate answer. It's a step in the right direction for us. We're slowly getting there, but it's not the ultimate answer. Is getting rid of RAP and RAS, recycled materials, is that really the answer? We've cut back on that a lot just to try to address some of the durability problems, but it's really not been the answer, and from a sustainability standpoint, it's really definitely not the answer. We'd like to be able to use those materials. We just need to use them correctly. You know, we throw around this term, use them but don't abuse them, and that's kind of where we got ourselves into a situation a few years ago where we were being abused with the recycled materials. I think we're using too much and not enough virgin binder in some of our mixes. So is disallowing modifiers like Recob and PPA the answer? We definitely have limits on those, but we don't eliminate them. We don't disallow them because I know they've been used in binders for a long time. It's really trying to find binders that are compatible with whatever you're adding to them, whether that's any kind of additives or modifiers. So we knew that we've got to be able to control those amounts, but we don't necessarily need to eliminate them. And really, the obvious question is doing things the same way we've always done them, the answer, and that's evidently no. So, and we really wanted to come back and tie that design somehow into more of what's going on with the pavement and a pavement design itself. And so we talk a lot about how does that tie into traffic, climate, some of, and those issues revolved around a pavement design. So in other words, you could have a great design, perfect design, but if it's not put in the right particular place in whether it's got traffic or whether it's got some adverse weather conditions, north, south part of the state, those things needed to be tied together a little bit more. And looking at volumetrics, like BMA, what are the important volumetric properties? I know volumetrics is important, but do they really need to control designs without regard to some of these other things? So these are some of the questions that we were asking ourselves and trying to get answers to. So really it comes down to we've got to stop using the recipe to determine if the cake is good. Define our expectations and open up the recipe to meet the end result. In other words, I think about cake. What defines a good cake? If it tastes good, what defines a good mix? Is it got lasting performance? Is the traveling public, getting what they paid for and enjoy the ride and the quality of the product? So, and really it depends. If you look at the top picture, if I go to a 5-star restaurant, that's how I define good. If I'm going camping, the bottom picture with the little Debbie's, that's how I define good. So depends on what roadway you're going to put that on. So idea is use what works, eliminate what doesn't, be simple and practical. So we started talking to a lot of our contracting community about this, and really it came down to this: what we need from a design mixture and what the contractors want. And really what we needed was we need to start designing for performance, for quality instead of economics. And what the contractors wanted was a level playing field. And so we're trying to figure out how we can do both of those things and still get a quality product out there. So when we looked at this balanced mix design approach, we were just trying to define what that really meant. So really we just kind of defined it as a way to optimize the mix to provide needed performance between stability and durability. And I'll talk a little bit more about that, and we'll get into the details of this now. So when we look at mix performance evaluation, this is really the key part of what we're calling the optimized mix design or balanced mix design. And that's between stability or resistance to rutting, as some people call it, and durability, which is some form of cracking resistance. And depending on where you are, there's a lot of different tests that you can use to provide an idea of rutting resistance and cracking resistance. And really you define that based on what's going to work in your area. I'm not saying that we have our own approach, and I know there's some other approaches out there that other states are like certain tests. So, but for us, it's finding a balance between both of those. And in the for our approach to optimize mix design, it's really for stability. We're looking at the Hamburg wheel tracking device. We've used that for years. We have a lot of data with that. And so we feel really comfortable with what we were getting from that test. For durability, we're looking at the overlay test. And that overlay test is we've done a lot of work, and there were some issues around the variability of that test. And I think I'm going to show you a little bit of work that's been done by the University of Texas, El Paso, some of the work they've done to try to resolve some of those variability issues. So I'll spend a minute talking about that a few slides from now. But the idea was we really couldn't do balanced mix design or optimized mix design without having both bookends. We felt really comfortable with the Hamburg, but for the longest time we had issues with the variability in the overlay test. So until we got that resolved, and we were a little bit hesitant about moving forward with this approach. This was some work that we had done several years ago, and just starting to get the idea of how the mixtures behaved. And this is asphalt content, and then you're plotting this for that left side is the Hamburg rut depth, and then the right axis is the overlay. So as you can see from the graph, when you add more asphalt, your Hamburgs get worse, your overlays get better. And just so you have an idea about the overlay test, the overlay test is sensitive to binder quality, but it's a lot more sensitive to the quantity of binder. In other words, softer binders on from a 28 is always going to perform a little better than a 22 binder on the bottom end. But what really drives it is that asphalt content. The more asphalt we get in that mix, the better the overlay number gets, and you can see that from here. So the balance here is not where these things cross, because they're obviously on two different axes, but it's that point where you set the thresholds. And in this case, we've got 10,000 passes on the overlay, 300 cycles on the overlay, 10,000 passes on the Hamburg. So that optimum, or that range, is going to be between 5.3 and 5.7 on AC content. Now, that, there's a lot of other things that go into that as well. And then you say, well, okay, well, if I give this to a contractor, he's going to obviously go down to the 5.3. Well, we were kind of thinking that maybe the engineer should make that decision based on what that mix is going to be used for. It's going to be an inner layer where you've got, some issues with, reflective cracking. Maybe you're going to move toward the higher range, the 5.7. If it's something where you've got a stabilized base or stabilized subgrade, we've got good structure underneath, you might want to go, and you've got some truck traffic, you might want to go to a little bit the lower side. So it gives you some flexibility depending on what you're going to use the mix for. So this is another example that some of the stuff that we're already kind of doing in Texas, and we've got a particular mix called limestone rock asphalt, and it naturally occurs. It's a couple of huge quarries in South Texas, and there's actually asphalt inside the rock, and they use a flux and they bring it out, and we use it a lot for patching and for repair work, and so we were having some issues with durability, and we have a beam stabilometer to do the stability, to test for stability. So everything was meeting stability, but we were having issues with raveling and oxidation of this mix. So we started to do the Canabro, and that's the kind of the balance between those two. And this is an example of the data from one of the types of mixes from that LRA. So it's just a different way to look at this, but still the same kind of approach. So we're balancing between stability and durability. And then we, where we set that threshold at on the Canabro loss is really defined. But you're trying to eliminate, sorry, I'm going to go to this marker here. There. Yeah, we're just basically trying to eliminate this material up here. So this was some of the mixes that were giving us problems for this LRA. So you kind of get an idea that's another way to kind of make this balanced mix design approach work. If you look at the larger picture of the framework that we've kind of come up with, it's broken into several categories. You've got material selection, and you've got, of course, the volumetric portion of that, which is optimizing your job mix formula. And then we've been talking about mix performance evaluation, and then of course workability. And so I just wanted to talk about a couple of these things in particular to say some of the work that's been going on to try to address some of these other issues. So we've always got to have a concern on what aggregates we use, and we have an aggregate classification system, which we call SAC, and determines what we're going to use for frictional properties. So we can't get away from that. We're going to have to make sure we've got good frictional properties on whatever aggregate we use for our mixes. So that's going to have to be addressed. For binders, modifiers, and additives, we started to look at, so when we looked, so let me step back just for a sec. When we started seeing issues with some of our binders, and we noticed that it was some things going on with the recycled engine oil bottoms or PPA, we were starting to see these things pop up in some of the binders. We realized that when we went back to address those, that they were all meeting PG specification. And so it wasn't really addressing the quality of the binder. And so there's some research now going on within Texas where we're actually saying, what's a good test that we can actually, that will actually give us a kind of qualitative measure of the binder? In other words, we need to make sure that even if it meets a PG spec, that it's going to be a good quality binder for long-term performance. So one of the things that we've really looked at is this delta T sub C, which is critical temperature on our BBR. And I've got a slide on that in just a second to kind of explain that a little bit. And some of you guys may already be aware of that. And then, of course, there's been a lot of work on MSCR, and we're really looking at MSCR as well to kind of indicate that, as well as some other tests. But something that's got to be there that will help us define that, the quality of the binder itself when we use it in a mix design. And so the main idea is no matter how you mix these products together, that we've got compatibility. And I think that's really where we're at, is trying to find the, binders that are compatible no matter what additives you're putting in there. So, and this is a little bit of the explanation on the delta T sub C. So when you run the BBR, the bending beam rheometer, you're getting two values. You're getting a stiffness value, which we call S, and you're getting a slope, which we call M. And you can obtain a base temperature for S and M. And so whichever temperature is higher is the one that we always say that controls. And so, but what we started to see was when we saw big differences between the S value and the M value, kind of defined as greater than 6 degrees. I've seen some work out there that's saying 5 degrees. But regardless, when you start to see a big difference in temperature, we started to see issues with the quality of the binder. So that's one of the things that we're really focusing on here as well. It's just a piece that goes into the puzzle that we're looking at this whole framework. So as far as optimizing the mix design, as far as volumetrics, we really got to have some kind of way to make sure we're optimizing our gradations. When we've moved to super pave, there was a lot of contractors out there that would, because they design their own mixes, and they were used to putting the mix, gradation through a really small band of, gradation band. And so now when you go to super pave, of course it's wide open, and so they're really struggling on how do I optimize this, gradation. So there's some methods out there. I'm not saying this is only one. I just have this that we need to somehow make sure we're optimizing our gradations as well. And then of course to give us the right volumetrics. And what does that look like? VMA, air voids. There's a lot of things out there. I like VMA, but we've got to make sure we're getting the right properties to make sure we're getting the good JMF and good volumetrics. And then of course we've talked about this as well with the mix performance between stability using the Hamburg and durability using the overlay test. And the more we got into this and started applying it to a few jobs, and like I said, we're still in the phase of where we're in research and we're actually doing some test projects. But we thought about it this way, if you've got a mixed design, and a lot of contractors, at least in Texas, they're pretty stationary. They have the aggregates that they normally use, and so it's a set of given materials that they're constantly going to make all their mixes with. And so if you kind of know what you're doing as far as what kind of materials you're going to have, then you've got a handful of mixes that you're going to produce every year. And so we thought this is an opportunity where if you've got a certain mix design and you say, it's almost like going to the doctor. If you're going to go to the doctor and say, doctor, I'm thinking about running marathons, or I'm thinking about taking up, swimming, or whatever the sport is, and so, well, the doctor's going to give you a checkup and say, are you ready for that, or you're not ready for that. So that was kind of the idea. It's like you could take a mix design, send it in, and we do this kind of checkup on a mix, and we go through the Hamburg analysis where we can plot out the number of passes versus the rut depth, and you can kind of get an indication if there's a case for stripping, and you can, of course, what the issue is. So every time we run Hamburgs, we say, okay, it rutted, or did it rut and strip, or did it just strip? So there's an indication there that'll tell you what's going on with it. When it comes to the overlay test, we had our previous methodology, or the way we interpreted the data, was something like this. You take that initial load, and then from the load, you 93% reduction of that. When the cycles hit that's when it cut off, and the number of cycles it took to get to 93% reduction would be, man, getting a lot of noise.
Robert,
yes.
I know I'm not quite sure who's speaking. Can you guys just please be sure to mute your phones for just a second? We're hearing a lot of background noise, and I'm not sure. I don't think that's on my end or Robert's end.
Not on my end.
All right.
Somebody's having a party.
Yeah, I still hear it, and I'm not quite sure who it is.
Well, I'm going to try to plow through if that's all right.
Go for it, Robert.
All right. So we had this initial, this is where we had started to run into a lot of variability issues with the overlay test. And so we were taking this 93% reduction of the initial load, and then that's the number of cycles. The number of cycles it took to get there, that's where we ended the test. And so you end up with a number of cycles. But what was going on was we were kind of ignoring the fact that there was a difference between the crack initiation and the mechanics that go on with that, and the crack propagation, or how the crack grows, and the mechanism that goes on with that. And so once that the work that they did at University of Texas El Paso, once that they started to separate that, our coefficient of variation came way down. And so we were able to define that test with two different parameters. The initiation of the crack, we just used a critical fracture energy, which is that area under that first. That's just the hysteresis loop here. I'm going to go to the pointer. That's just this first cycle hysteresis loop. And then this is the crack retardation rate, or the crack progression rate, and this is just a drop in load between consecutive cycles. So once we separated those out, we were able to kind of better define our mixes. And I'll show you a plot here. There we go. So these are all the different mixes, rated basically the most flexible mixes, or the most crack resistant, down to the least crack resistant, at least in our opinion in our experience on the mixes. This is a crack attenuating mix. That's what that stands for. The TOM is the thin overlay mixes. We've got some SMAs, you guys know that, and then our super paves, and then these are our regular dense graded mixes at the bottom. But you can see the tougher it is to initiate that crack, that's that critical fracture energy, or on the y-axis, and on the x-axis is the crack progression rate. And if you go back toward the left, that's actually the more flexible that is. So this gives us an idea of where our mixes currently are, and this is without any optimization, but just kind of we wanted to take all the data that we had run previously and plot it out to see kind of where we were. So now the idea is, not that these mixes are good or bad, but what mixes can be used for what types of roadways, or what types of solutions when we put that, plans together and put pavement structures together. And also the idea here was, okay, so I'm in this area here with the Super Pave D. How do I move this mix from here to here? What do I need to do to get this from, this quadrant over to this quadrant? So this is some of the work that's still ongoing, but kind of the idea is how do we get these mixes to be more tough to crack and more slow to crack, So that's the idea behind the new overlay work that's been done at the University of Texas El Paso, and so there's a lot of that work's coming out as well. So we said, okay, we've got a lab standard mix that we use for a lot of different internal research. We thought, well, let's just put it to the test and see where it falls. And so we kind of ran both this new data analysis on the overlay test and the Hamburg itself, and plotted out. And there was some slight stripping in the Hamburg, and we addressed that with some anti-strip, and it barely failed. So like I said, we at 15,000 passes, it barely failed. So we wanted to do a little bit. So it was a little more rut resistant than it was crack resistant. If you look at the numbers, it's in the right quadrant that we wanted it to be in for crack resistance. So we were just trying to see where we were at on that, and just to give us an idea how the thing would work. So some final thoughts. I think some form of balanced mix designs is definitely going to be in our future. We've got a lot of research and a lot of pieces to that research that are being put together toward this. There's a lot of things going on a national level already that looks like that's the direction we're headed. So, the constraints for us, and when we talk about this with the contracting community, one of the things we said, we'd like to get away from all the, detailed specifications, and really telling the contractor exactly what we want and how we want it, and all these parameters that we're trying to define, and so it gets really restrictive. And so the idea is to take that all away and really look at the performance tests like the Hamburg and the overlay, and some form of volumetric would have to be in there. And of course you've got aggregate and binder, some kind of quality properties that indicate that you've got good materials going in. So we know that that's a slow process for us. I mean, we're a DOT, and I'm not going to pretend that we don't have our own bureaucracy, but it takes a little while to get that. But it is, and we've got to change our thought process, how we look at the balanced mix design approach, and giving that control over to where, okay, contractor, I don't care about all the other things. I just want something that's going to perform, And so with that, that's all I have with that. I guess we will open it up to questions.
Yeah, I had taken it off of mute, so if you all want to just speak your questions, you can actually, there's a raising hand, you can raise your hand button next to your name and we can call on you, or you can just chat your questions in the lower left-hand corner and we'll be happy to get to those. And I won't call out anyone by name, so if you're concerned about that, you have full anonymity here.
Okay.
Anyone? I don't see anyone yet. Robert, do you?
No.
Okay. We have a question coming in that asks, how many replicates do you use for the HWTD and DOT?
Sorry about that. Go ahead.
So how many replicates do you use for the Hamburg and the Texas overlay test?
We use 2 for the Hamburg and 3 for the overlay.
Okay. Who else?
One of the things too I wanted to mention, Amy, was to the group, is that we had looked at some other cracking tests. We really liked some of the work that Louisiana did and is doing with SBC and then or SCB, and then also Illinois is doing a version of that as well. The reason that we like the overlay test is that it's a cyclic test, and instead of a monotonic test, and the cyclic test is being able to give us the coefficients that we need to put into a pavement design program. So when we start running a version of MEPDG, then we can plug those parameters in and have material properties to go straight into a pavement design program, which is really nice.
Robert, can you answer the question, why 2 tests for the overlay tester?
I guess that, well, and maybe I misspoke, but we used 2 pills and then we cut them and then butt them up together. So that's really, I should have clarified that.
Okay. We have another question. I've got a couple coming in, so we're going to get these one at a time. The first one is, do you use slabs in the Hamburg wheel tracking or gyratory pucks?
Yeah, we use gyratory specimens. Yeah,
okay.
and I probably should have clarified that. So we use gyratories, 75 millimeter height, and cut the ends and butt them together to make basically equivalent of a slab.
Okay, and we have another question that is maybe a little bit slightly off of this topic, but they're asking if you could talk about the friction requirements and how that affects the balance mix testing.
We have a system to where we qualify all of our materials, and we have it's called a quality monitoring program where we monitor all the quarries around the state that are used, and so they have to be on the program and approved. But we basically, through testing, and it's acid insoluble, and then we'll run soundness and LA and microdeval. We run some other tests, but really the acid insoluble determines whether that material is going to be able to be a Class A material, which is what we use on all of our high friction surface material, or Class B. We're in the process of looking at a kind of a B plus, where we've got a little bit better quality B aggregate that could be blended with an A. But that's ongoing research that we're starting to look at now. Did that answer the question?
I believe so. We gotta thank you. So I
Okay.
think we're good.
All right.
I did note that someone who's dialed in on the phone showed their hand raised. So if you want, you're welcome to just vocalize your question. And perhaps we've answered it. What other questions do we have at this point? Any other hands or anything else we can answer? Okay, if there's nothing else right now, I will just let you know that for all of you who are on the call today and have participated, we will be providing professional development certificates. So those will be emailed to each of you individually. So please look out for those. If you do have any questions, you can feel free to reply to me, Amy Chiconis at Ingevity, when you receive your certificate. We thank you so much again for joining. We thank Robert for taking the time to speak to us. And actually, one more question. I'm seeing a couple of things are coming in before we end, if that's okay.
Sorry.
We have someone asking, what is the VMA requirements for the other DOTs?
Oh, yeah.
Maybe perhaps that's a question to some other DOTs that are on the line. I don't know how best we can answer that.
Yeah, ours is different for every mix, and it's also different from design to production. So it's a percent lower on production than it is on design. And I don't know if that's a good thing, but that's the way it's kind of set up with our mixes. So.
Okay. So we have another question from someone else asking for you to please discuss the overlay tester, perhaps in a little bit more detail if you can.
Sure. Yeah, the overlay tester, and maybe I can go. The overlay tester was, I guess it was developed by TTI quite a few years ago, and it basically is a test to really look at, it started out as looking at fatigue cracking, but ended up really kind of morphing into, it was a good indicator of reflective cracking as well. We take a molded specimen and cut it into a shape. Well, let me go back to this slide here. You can kind of see on this, from this picture, if you're still online, we cut it in this shape and then we glue it down on these plates. And in the normal overlay test, which is run, and this is on the AMPT, which has a fixture to be able to run it on the AMPT. But we have another machine that's just a dedicated, a couple of them, overlay machine that runs in the horizontal position. One side's fixed, the other side moves, and it just basically is opening up a very small rate, and you're initiating a crack and propagating that crack up from it usually starts at the bottom and works its way up. And then the original work was that initial load that you got from the first cycle, 93% reduction of that. How many cycles it took to get there, that's what defined the resistance of the cracking resistance of the specimen. So that's kind of the premise of the test. And over the years, we really liked the way that the overlay test differentiated between good and bad mixes, but we had a lot of variability between replicate samples, and that's where we struggled. When you're running a bunch of data, you get really good information out where different mixes perform. But when you run triplicate samples, and we were seeing 10 cycles, 200 cycles, and 750 cycles, you're like, which one's right? Well, that just throws a lot of confidence goes out the window when you start looking at that and trying to figure out what the real number is. So that's where we've kind of come back and looked at differentiating or separating out the crack initiation from the crack propagation. Hope that answered the question.
Okay, I know we had kind of an influx there just a minute ago. Are there any more questions? I don't think I see any other hands raised, and I don't have any more questions in our chat area. Oh, I see a couple more actually. Okay, did you say 3 replicates for the overlay tester and 2 for rutting?
Well, it's really 2 specimens that we make for the Hamburg for rutting, but we cut them and then put them together in a mold. But you're right, correct. It is 3 replicates for the overlay test.
Okay. And we have another question asking if your overlay tester specification is available.
It is. It's on our website, but that's probably
if you'd like, Robert, when I hand out the certificates, I'd be more than happy to include that in the email with the certificates to each one of the participants. Is that all right?
I'll send you a link to it, Amy. Then you can put it in there. So,
great.
And be aware that it's the old spec. It's going to change.
Okay.
It's going to change to the new method. We can't until we're completely ready to switch over. We still have to leave the old the old test procedure in there. So.
Okay, wonderful. Awesome. I think that looks like it's it for now, unless we have anyone else. I think we answered everything. So again, thank you so much for your participation. We will be distributing the specification for the overlay tester along with the email that you received for your certificates, and this recording and the slides will be available in a link that I will also include in the professional development certificate. So it'll be on our blog and on the site that we have specifically for connecting the dots. So thank you so much for your participation. Have a wonderful afternoon, and we look forward to hosting you again soon.
Thank you.
Thank you all.